Howdy, my name is Paul Terman, and I'm from Texas A&M University. This is the point in time where I'd normally have that howdy shouting match with you guys. But this talk has actually been pre-recorded, so I won't be around to answer questions later during the live question answer period, but feel free to email them to me. My email is provided. I'm going to talk to you guys about how we've used machine learning in the LUX detector in our search for lightly ionizing particles, also known as LIPs, also known as fractionally charged particles, which have a charge less than that of an electron. They come about in a variety of dark matter theories and also non-dark matter theories as well, such as theories dealing with magnetic monopoles, where the monopole will actually get a small electric charge under the Witten effect. String theory and multidimensional scenarios, and other scenarios where we have a hidden U1 dark sector, the lip comes about as a dark paraphoton as a result of what we call kinetic mixing between our U1, electromagnetism, and the dark U1. Lips come out in questions of charge quantization within the standard model, and other questions such as the neutrality of the neutron. And of course, in our search for dark matter, we want to leave no stone unturned. This is what I call the WIMP parameter space problem, because as you can see, as we keep pushing lower and lower in the WIMP parameter space, we're getting closer to this neutrino floor. This graph shows the projected sensitivity of LZ, that's LUX's big brother, which is about to go online. And as you can see, we're getting very close to that neutrino floor, where we wouldn't be able to tell the difference between a WIMP and a neutrino. We need to start looking elsewhere. The LUX detector is actually a retired detector filled with over 300 kilograms of xenon. It's a dual-phase time projection chamber, a TPC. What that means is that a particle comes in, smacks into the liquid xenon. We're going to see an initial burst of light. That's going to be our S1 signal. At the same time, xenon is going to be ionized. There's going to be cast-off electrons that will drift through the gas-liquid interface from our applied electric field. When they reach that, they'll be extracted out into the gas, producing a much larger signal. That is our S2. And it's the timing between the S1 and the S2 that gives us our Z position in the detector. And this is all read out by two arrays of 61 PMTs, both above and below the detector. It was located in Surf in South Dakota, about 1 mile underground. And of course, it was designed and optimized for WIMPs, but we can reanalyze the data to look for these lip signals. And what would a lip look like? Well, there would actually be two different tracks. That's right, tracks, not individual hits, as we would expect from a WIMP. The first type is where we see a bunch of discrete hits along the detector. Could be dozens of hits. We've actually increased the amount of pulses allowed in the data processing framework up to 100, which is much higher than the normal amount of 10 pulses. The other type of lip signal is where we see a long block of ionization, much similar to a muon that's cutting through the detector. And what we've done is we've implemented the first use of pulse chopping, where we've cut off a small portion of time for the S1, and then we've cut the rest of the physical extent of the detector up into 99 equal parts for our S2s, and we're able to send those through our data processing framework to get all of the information we need. We simulated LIPS using the JAONT4 monopole class, where we've turned off the magnetic charge, and then we're able to play with that electric charge. It's actually an extension to JAONT4, but it's able to be incorporated into our simulation package. We've simulated things in the range 0.01 to 0.3 charge. We've analyzed the data in two methods, both using a test set of data of 14 days out of our 86 live days, where we assume that there is zero signal. We then develop a number of cuts. These are more of a traditional method. Here I show you the chi-squared. It's the goodness of fit for the track. As you can see, we can separate the live data, which we are treating as background, and the simulated data, which we are treating as signal. But that's not why you guys are here. We're here to talk about machine learning, specifically boosted decision trees. We've used the scikit-learn package and AdaBoost in Python. And the way that a boosted decision tree works is that we get a tree model that we train on our data set. We test that. We tested things actually with a 70-30 train test split of our test set and simulation set. AdaBoost then focuses more on those things that it misclassified, putting more weight on them, and then it retrains the model, getting a new tree, and so on, iterating until we've reached desired sensitivity without overtraining. We've actually made two different types of boosted decision trees, one using 7 parameters. That's the 6 parameters that we've made cuts on in the traditional space, plus the notion of chopping, so 7 parameters. And then we've opened up the boosted decision tree to allow for 71 parameters to really push how far we could get those BDTs to go. Now, in implementing the boosted decision tree, we actually ran several thousand BDTs using that 14-day test set. We looked at what the live leakage is in the predict proba space. That's the number that is generated from the program that is between 0 and 1, determining how background-like or how signal-like a particular event is predicted. We made a cut not at 0.5, but we biased it a little bit to 0.54, where we determined that applying the BDT to the entire live data set predicts 0.1 live events leaking through. We wanted to be very conservative and force the BDT to not have any live events in the signal region. This was out of an abundance of caution to prevent leakage. We used the BDT, the final BDT that we used had reached 0 live events the soonest. It did so at 0.52. We did this, again, out of an abundance of caution. However, that did seem to affect our simulation efficiency slightly. We had an overall efficiency of approximately 69% of those events with tracks at the 0.54 level, which was slightly below the cuts method, which was around 73 on average. We saw that the chi-squared, which was that parameter that I had shown you in the cut space earlier, was the most important of the features in that BDT, that final BDT, which lines up very well with what we saw and expected using the more traditional method. Again, verifying notions that the BDT is showing us things that we would expect. And now we have this more comfortable picture of BDTs, that they're not differing too much from what we got using the traditional method. We then opened it up to 71 parameters. Here, we did train several hundred in order to determine where to draw the predict proba cut line. As you can see, the bimodal distribution on the right here from the 71 parameter BDT, they are much further spread apart, the two modes, with a much longer and thinner tail. We actually decided to draw the predict proba line at 0.56 to have the same 0.1 live leakage events predicted when applied to the entire live data set. But our simulation efficiency rose to 90%, which is a huge success. 90% of those with tracks. And we placed no further considerations or constraints on the BDT like we had with the 7 parameter. So what does that do for our efficiency? Here are the 3 methods summarized for our simulation efficiency. We've got our orange line here. That is our data selection cuts. That's our traditional method using the 14 days. We then have the purple line here. That's our 7 parameter BDT. It's slightly worse. This is a log graph. This is slightly worse than our traditional method. But as I had said before, it gives us a feeling of comfort that we can rely on the BDT, that it's not just some black box, that it's matching or close to matching what we would get from normal or traditional methods. And then Our green line is our 71 parameter BDT, where we see an improved simulation efficiency overall, with the exception of the 0.3 charge, which is the highest charge on the left here, slightly below the CUTS method. That's probably because we had fewer 0.3 charge sims than all the other ones. So what does that do to our final flux? We want to have the lowest flux possible. And as you can see, we have the fluxes plotted for the 3 different methods, the CUTS and then the 2 BDTs, with our 71 parameter being the dark blue line here, which is below both CDMS's LIP result from several years ago and Majorana's result from 2 years ago. We can't really compete with some of the larger scintillators, but those are for much higher charges. In the mid to low charge range, we beat out all of the competition whole-handedly. And of course, this was done finding no candidate events in the range 0.01 to 0.3 of the electron charge using our flux equation here. So I'd like to thank you guys for coming to my talk, for sticking it out towards the end of the second day of the conference. Like I said, I'm not going to be around for live questions, but please email me. My email is provided in the slides. If you want to hear more aspects of the LIP analysis, because I talk about things not just related to machine learning, but if you want to hear more, I've got 2 more speaking engagements coming up. It should be really exciting. Again, thank you guys, and have a great day. Be well.